I'd like to thank the organizers for inviting me here. As someone who started mathematical research just before H&M and BCHM and so on, the ideas of many people in this room have made my mathematical journey exciting and really, and I can't say how indebted I am to the collective in this room, to Berka, but as well to Professor Mori, to CHM, and to all the others in the room. So thanks a lot. So what I would like to talk about today is a couple of projects related to K-moduli spaces of Fano threefolds. So I suppose I would like to start by saying, colloquium style, that there are deep interactions between differential geometric properties or analytic properties and algebraic geometric properties of Kähler manifolds. So perhaps the standard example of this, or the first occurrence of this, is what Carolina mentioned this morning, with the Poincaré uniformization theorem. So in complex dimension 1, if I consider compact Riemann surfaces of genus greater than 1, then the existence of a Riemannian metric with constant scalar curvature -1 turns out to be related to the existence of an embedding as a GIT stable curve. And this correspondence still works with moduli constructions. So so this correspondence extends to constructions of compact, or constructions and compactifications of compact moduli spaces for curves of genus G. So by this I mean that you have this analytic or differential geometric construction as a quotient of the augmented Teichmüller space. On the analytic side, so the quotient by the mapping class group, so this is your degenerating metrics, hyperbolic metrics on the one side, and on the other you have this Deligne-Mumford compactification, so the Deligne-Mumford construction of the moduli of stable curves. And so these two turn out to be canonically isomorphic. The two compactifications you obtain by, on the one hand, considering the analytic story, and on the other, considering the GAT, the Lin-Manford compactification. So these two moduli spaces, these two compactifications, so where on the left-hand side you're degenerating a metric, on the right-hand side you're degenerating a curve, end up being canonically isomorphic. So let me now kind of step back from complex dimension 1 and talk about a special class of Kähler manifolds, or rather about Fano varieties. So as we've seen in Carolina's talk, or as Carolina explained this morning, we have this notion of K-stability, K-polystability, which was really introduced originally, historically, to kind of characterize the existence of these canonical metrics on Fano varieties. So K-polystability, or introduced as a characterization of the existence of Kähler-Einstein metrics on a Fano variety, or on Fano varieties. So here I'm not giving very precise references, but that's the Yao-Tian-Donaldson conjecture, later proved by Tian and Chen-Donaldson-Sun, and there's been some extensions of this result to singular varieties. So K-polystability is equivalent to the existence of a Kähler-Einstein metric. So, so that part of the story is beautiful in itself, but I'd like to talk about like some consequences of that. Or so for a very long time, it was thought that the moduli of Fano varieties was very pathological. So the moduli functor is not separated. The usual higher dimensional constructions of moduli, or the usual constructions for higher dimensional varieties, do not extend to Fano varieties. But we know that there is a moduli space for Kähler-Einstein metrics. There is an analytic construction of a moduli space for Kähler-Einstein metrics on a manifold or on a variety. So perhaps it shouldn't be that surprising that there is an algebraic counterpart to this statement. And so this is, I guess, the work of Chen Yang and many of his collaborators, who have established in the past few years this amazing result that there is a projective good moduli space MNV K polystable, whose closed points parameterize K polystable Q Fano varieties of dimension n and volume V. Okay, so this is an amazing development, and even though yesterday Kristen mentioned that in the case of canonically polarized varieties, we actually know no example. So we know a few examples in this case, but not so many yet, although that's a very active area at the moment. So, boundedness, I feel like I'm cheating a bit because we've known that there's finitely many deformation families of smooth Fano threefolds, dimension 3 for quite a while. But I'll just say that by boundedness, we know that in any dimension n, there are finitely many deformation families of smooth Fano manifolds. Okay, so perhaps what I'd like to, or let me perhaps say that in dimension n is equal to 2, as Carolina mentioned this morning, we know that there are 10 deformation families of del pezzo surfaces. In dimension n is equal to 3, we know that there are 105 deformation families, and these were classified. I'll come back to that classification. These were classified in the early 80s, I suppose, by Iskovsky in Picard rank 1 and Mori and Mukai in higher Picard rank. So the goal of my talk today is, can we describe some components of these K-moduli spaces M3 DKPS for suitable V's, for suitable volumes, or can we describe some components or the components containing smooth members, smooth Fano manifolds, or smooth Fano threefolds. Okay. So I should perhaps say that in dimension 2, so in dimension 2, the entire story is known for smooth del pezzos. So this was work of Mabuchi and Mukai in degree 4. and then work of Odaka, Spot-Jensen in all degrees. So d equals to 4 was described by Mabuchi and Mukai, and any degree was described by Odaka, Spot-Jensen. But in both cases, the proofs rely on the analytic picture somehow, the degenerations of metrics at some level. In dimension 3, a few examples are known. Notably, the case of the cubic threefold. So cubic threefolds were described by Liu and Xu, who showed that the K-moduli space of cubic threefolds coincides with the GIT moduli space of cubic hypersurfaces. But it's known that for other degrees, for other hypersurfaces, the same does not hold. So what I'd like to do is to give some other examples of constructions of K-moduli spaces. So perhaps a motivation for this is to try and understand a little bit better a geometric meaning of K-stability. At the moment, we have had in the past few years, due to the work of Xu and his collaborators, we have a completely algebraic reformulation of this K polystability notion. We have these valuative criteria which are incredibly powerful. But in terms of explicit threefolds, it's not always very easy to see what this means.
What do you mean by describe? Like, you actually give equations of the parameter space, or?
No, I'm gonna say that the one-dimensional ones are isomorphic to P1. So they're smooth. There's complete spoiler, but yeah. So I'll explain in a second. Yeah. So perhaps let me come back to the classification. So Carolina mentioned this morning the classification and referred to the phanography. But I guess what this classification does, it's quite explicit already. So you should. It's surprising to me somehow that we know so little about moduli when we know so much about this classification. So this classification, I'm not going to talk about the case of Picard rank 1, but in higher Picard rank, this is essentially a birational classification. So what Mori and Mukai did was classify the extremal rays of those Fano threefolds, and so get a classification by basically describing the projective morphisms to other projective varieties. And so you have this extremely explicit description, but this classification is not modular. So it doesn't tell you which of these beasts are isomorphic to each other, for example. But it is a starting point from the point of view of moduli, because it does suggest parameterizations of these families. So from this, you get parameterizations. And with a bit of work. And you also get the dimension of the moduli space, because essentially you can count parameters. So dimension of moduli space, or dimension of moduli space if not empty. And so as Carolina mentioned, the work of the first Fano team. So for the Fano book, we know which of the 105 deformation families have non-empty or have K polystable members. And hence correspond to a non-empty component of the K-moduli. So here I'm lying, but just a bit. We need, for this non-empty component of the K-moduli space, there's the extra case. There's the one family which has K semi-stable but non-K polystable members that also gives me a non-empty component. And perhaps I'll say a few words. So this is the example that Carolina treated this morning. So what we know is that 26 families give an empty component, so they are K unstable. They consist entirely of K unstable members. One family, this is Morimukai 226, has one strictly K semi-stable member. And then the other 78, they have a K polystable general member. Okay, so how bad can it be? So among these 78 families, or maybe, so here, let me just say I want to describe, describe components of low dimension. Because nothing can be too low, I'm going to start with 0 dimension. So, so in dimension 0, so dimension 0 of moduli dimension 0, we have 44 families out of the 105. And out of these, yeah? Yes, we do, but I haven't counted them. Yeah, yes. So in the phanography and in the book, you have a description of automorphism groups. And so those that have finite automorphisms are then K-stable. So here you have 44 families, and out of those 44 families, there's 20 which have which consist of one K polystable member. So these so for these 20 families, the associated component of M3 V KPS is just that point. Then we have the family that Carolina mentioned this morning. So MM226. So in that case, if you remember, this was a family that was obtained by blowing up a line that lied on V5. And there were essentially two lines on V5, up to automorphisms. There's either the good lines, which have like balanced normal bundle, and then there's the bad lines that have unbalanced normal bundle. And as Carolina mentioned, so the good lines, blowing up a good line gave you this X1. And she constructed this morning explicitly a degeneration to this X0, which is not strictly speaking in my deformation family of smooth Fano threefolds, because it is a singular threefold. It is a complexity 1 T variety, and it is K polystable. So K polystable, singular. So these were strictly K semistable. And then we had these X2, which were K unstable, which corresponded to blowing up the bad line on V5. And so here, what's the moduli associated? So the component, let me just write down M bar KPS 226 is actually just this point X0, which is not itself in the family. So this is the unique K polystable limit of singular K polystable limit of smooth members of this family. And so the other 23 families, they don't have any K polystable member or K semistable, so they correspond to empty. The corresponding components are empty. So the 23 others empty, so have no K semistable members. Okay, so so what I'd like to do next is look at the components of K-moduli space, spaces that correspond to the one-dimensional or the one-dimensional component of K-moduli space. So what about one-dimensional components? But if you go to the classification, you'll find that there are 8 families which have one-dimensional moduli. And out of these 8 families, we have 2 that have no K semistable member, so all members are K unstable. So two families with only K unstable members. So these give you empty components of K-moduli spaces, and 6 families with K polystable general members. So the result I want to discuss, which is Fano team 2, says that the components of M3V KPS corresponding to these 6 families are all isomorphic to P1. And as a corollary of the proof, we identify all, all singular K polystable Fanos that are limits of smooth members of these 6 families. So identified all singular K polystable Fanos with a smoothing in these families. So this is essentially a corollary of the proof. So perhaps before I give a description, or maybe I should start with a description of the families. So before I give let me give the description of the families first, and then will come the real answer to Christopher's question, I guess. So I'm going to not give too many details about these families, but so the first family is Morimukai 224. Actually, sorry. I'll perhaps start with the answer to Christopher's question. So I want to give a general scheme of proof. So in all of those cases, as I mentioned, we have this Mori-Mukai classification that gives us a possible parameterization. So the first step, which is essentially done in the book by Fano team. So the first step is to identify a parametrization of elements in the family of members in each of the families. So in this case, as I said, we relied on the work already done in that. And then the second step was to determine exactly which of the find. So this is, I guess, Fano team plus epsilon now. Find exactly which smooth members are K polystable. So as Carolina mentioned this morning, we know that for some families, we have both K polystable and non-K polystable members of the family. So in the book, we left as a, so there are, I think, 27 of the 78 families where we expect every member to be K polystable. And then we had left as a conjecture for 7 of the families. We had some conjectures about which ones were K polystable and which ones weren't. So 2 of those families are among those 7 conjectural pictures. And so we have now got a precise picture in this case. I should say that these are not the hard ones. So the mysterious ones, for example, V22, we know nothing more than we did 2 years ago. So I think in the case of Morimukai 222 and Morimukai 312, those were open there and are no longer open. Okay, so the third step, and that's where I guess comes the answer to Christopher's question. Is to find a P1 family so this is going to be a family over P1 such that, so I want it to be a Q-Gorenstein family. And I want such that for every K polystable smooth, or let me just say member of the family, there is a fiber. So every single smooth K polystable member of the family appears as a fiber in that P1 family. So I should say that in all the cases, in every single one of these families, of course, not all smooth members appear in the family. We are able, so the parametrization that we get in the book is often, oh, here's a parameter lambda that varies in A1, and then we have another like 3 sporadic cases, which we then exclude. So basically, in this P1 family, you will not find all members of these families, all smooth Fano threefolds, but you will find all smooth K polystable threefolds. And so once we have this, we need to study the family. So study the family. By this, I mean find all lambda such that x lambda is smooth. And find all lambda such that x lambda is K polystable. Because also, apart from in one case, we do have strictly K semistable fibers. We never, apart from the first family, it's never a family of K polystables. There's always at least some fibers where things are strictly K semistable. And so this is not supposed to be a super technical talk, so I will just say that we are able to show that, or I'll say that later. So check that this gives a map from P1 into the moduli stack of, or the component of K semistables So we have a P1 family whose fibers are K semistable, but most fibers are actually K polystable, and we're able, by general results here, or rather, I'm somehow packaging everything together in the interest of time, but so here what happens, perhaps not to offend any sensibility, is that we find that all singular, so once again here there's a slight lie, but that's fine. So all singular members have isolated terminal singularities, and they are K polystable. So these so this condition here allows me to conclude that these are normal, and they are one-dimensional. They are proper and normal, so they are, and that I have a surjective map from P1, so they end up being isomorphic to P1. Check that this gives a map here, which is surjective, and n bar Z is homomorphic to P1. So let me perhaps in the last 10 minutes, I'll try and not be too long. Just give a very quick description of some of the families and perhaps one example where in more detail. So I should say that the bulk of the work of that second work is actually showing that these singular members are K-polystable. But this is the technical bit, and yeah. So a quick description of the families. So the first family is Mori-Mukai 224, if any of you knows their classification by heart. Happens to be, so this is a net of conics. So net of conics, so these are nets of conics and I will not give the parameterization, but the second family, 225, is pencils of quadrics in P3. So in both those cases, we end up with very natural parameterization, and the picture ends up being precisely what you expect. It coincides with the GIT pictures for nets of conics or pencils of quadrics. The third family, which I think is my favorite, is Mori-Mukai 222. And this one is described as the blow-up of a rational quartic curve in P3. So there's actually two so here, let me just say, so here, as Carolina mentioned this morning, when you have the first number is the Picard rank. So if you have a Fano of Picard rank 2, you expect it to have two contractions, two extremal rays. One of these is to a curve C, which is a rational quartic curve on P3. A rational quartic curve always happens to lie on a smooth quadric. It's a 1-3 curve on a smooth quadric in P3. The other side is the blow-up of a conic of V5 along the conic. Conic in V5. I'm just mentioning that for later. But okay, so we find that you can parameterize all smooth K-polystable members of this family by looking at by taking a parameterization of C. So this is given by C lambda is ux square x plus lambda y equals to Vy square lambda x plus y. So this is in P1 cross P1. So here, this is with coordinates UV, coordinates XY here. And so here we have this parameter, this P1 family, which is given by x lambda being the blow up of P3 along the curve C lambda. I am not saying that this is the entire family. As a matter of fact, it isn't. But all the K polystable ones fit in that family. It turns out that for lambda not equal to plus or minus 1, x lambda is smooth. For lambda not equal to plus or minus 1 or plus or minus 3, x lambda is K polystable. X plus or minus 3 degenerate to x0, which is K polystable, so they are strictly K semistable. To x0. And x plus or minus 1 degenerate to x infinity, which is singular, corresponds to the curve that degenerates to a conic with two lines. So x infinity is the blow up of a curve which is just a conic in two lines. Ux minus Vy times x times y in there. Okay, so here, so we can show that x infinity is K polystable. It is singular. It has two ordinary double points. And so this gives you the Wald scheme in this case. Maybe what I'd like to say is, I'll say a few words about the next families, but what I found, the reason why this is my favorite example is because there are essentially, when we started thinking about this, there are two pictures. And of course, I wanted to start on the V5 side because V5 has a very rich representation theory. And so essentially, curves on lines, conics, and so on V5 are very well understood. There's a very rich representation. Turns out that trying to do the GIT of this conic on V5 doesn't give you the full picture. If you want to get the full picture from that side of the two-ray game, you really need to deform V5. But this K moduli space for those Morimukai 222 does coincide with the GIT moduli space of 1,3 curves on P1 cross P1 embedded in P2. And this turns up in the next two families. Because the next families very briefly, let me put them here. So family 4 is Morimukai 312. That was another one that was left as a conjecture at the end of the book, one of the 7 families that we couldn't entirely describe. And this is the blow up of P3 along the disjoint union of a twisted cubic and a line. But it's also the blow up of P1 times you can also describe it in terms of as the blow up of P1 cross P2 along a curve gamma, which is obtained as the image of a 1,3 curve in P1 cross P1 embedded in P1 cross P2 by the identity and the Veronese, second Veronese embedding. So you get essentially the same story as family 3. The same parameterization, the same, so now you take gamma lambda to be the image of C lambda, and everything works exactly the same as in the previous case. The 5th family is again related to this 1,3, and so it's Morimukai 413, and this also has something to do with 1,3 curves. And then the last family, which I just want to mention very briefly. So this is Morimukai 313. And so here, this is the intersection in, so this is a complete intersection of 3 divisors 110, 101, and 011. In P2 times P2 times P2. And the reason why I want to mention this one is that this was the one we couldn't do for a very long time. Because, and this is the one where what I said before is a slight lie. Because we are able to fill up A1 out of P1 with singular K polystable, singular or smooth K polystable that are easy to track, but then we're missing one point. And what happens at that point is that we no longer have a complete intersection in P2 cross P2 cross P2. Instead, we have an interesting Pfaffian variety which has a smoothing in that family. So I'll stop here, and I apologize for running over, and thank you very much for